the solution to this problem is something you wouldn't believe. This is 2, 8, 6, 7 count valid paths in a tree. This was the most recently released Leetcode hard, and it's definitely hard. It's definitely one of those problems where it takes some sort of intuition that may not be immediately transparent, and even if you find kind of the main component of the problem, there's also sub problems that you're going to need to solve in order to make your solution efficient enough to pass, right? So it's one of those things where it's like, oh, I realized how to solve this. Oh, well, now that I know how to solve this, that actually creates 2 additional or 3 additional sub problems that I need to figure out how to solve. So it's definitely an accurate classification. It's a problem that keeps on giving. You know, you say, I got you. I know exactly how to solve you. And then it's like, oh, well, now that you know how to solve this, why don't you solve this? I don't know if that makes any sense, but essentially this is a hard, and I respect that classification. Okay, so like most tree problems, right, it's going to be given this, you're going to be given this first kind of little paragraph about what a tree is and how it's provided to you. So there's an undirected tree with n nodes labeled from 1 to n. Okay, you are given the integer n and a 2D integer array edges of length n minus 1, where edges of I equals ui vi. Okay, so you're given all the number of nodes you have n nodes, and then you're given the edges that connect the nodes, right? So the links between the nodes indicates that there's an edge between ui vi tree. Return the number of valid paths in the tree. All right. A path AB is valid if there exists exactly one prime number among the nodes label in the path from A to B. Okay, so a path is valid if there exists exactly one. So not less than one or more than one, but exactly one prime number among the nodes labeled in the path from A to B. Okay, note that the path has a sequence of distinct nodes starting with node A and ending in node B, such that every 2 adjacent nodes in the sequence share an edge in the tree. So, you know, that's a very mathematical, technical way of describing what it's trying to say. But, you know, if you had a tree like this, you know, I don't know, right? There's no path like, or let's make another node. Right, first thing is you can't, like, a path from U to Z can't be like this. Right, because I jumped over U, VY, right? A path from U to Z has to go through UV, UVY, has to go to UVY, has to go to YZ, right? It has to actually traverse each of the nodes. You can't just, like, jump nodes, so that's what this is saying. And then path AB and BA are considered the same and counted only once. So what does that mean? Well, you know, if I go like this, that's one path. I can't then be like, oh, well, this is another path, actually. No, it's like, no, it's the same exact path, right? Now, note that a path is unique because there's no cycles, because this is a tree, it's not a graph, right? So there's no cycles in the system, so there's only one path from U to Z. And we can go through proofs about why, if it's a tree, there's no cycles, so then there's only one unique path from U to Z, but that's true, right? There's no other way to get from U to Z except for this path, because there's no cycle, because if there was a cycle, there'd be another path that I could get there from. But since it's a tree, there's no cycles. Okay. So let's go ahead and do an example. Now, one of the preliminary notes you should always be considering when you solve tree problems or graph problems in general is that it's not necessarily a binary tree. It's not necessarily a tree with a root, right? This is just a system of nodes that are connected, and the system of nodes that are connected don't create cycles given the way that they're connected. What I mean by that is, like, the way that this is provided, right, is it makes it seem like a binary tree or something. Maybe not a binary tree, but like a tree there has a root and then it has, you know, directional edges, but that's not necessarily the case, right? And you may not want to force yourself into thinking of the problem like that instantaneously, because that's going to lead you down a different path. Trying to think about, okay, how am I going to solve this solution? Thinking about it as a tree where there's a root and then there's nodes. Well, what would be the root? One's the root. Why is one the root? I don't know, right? So don't let yourself be tricked. Don't trick yourself by thinking, oh, since it's a tree, it looks like this, right? The tree, you can draw the tree however you want. There's no necessarily, like, upper level, lower level kind of aspects to this problem that you get like in a binary search tree, right? Because in binary search tree, you have like level 0, which is the root. Level 1 is children, the children, right? Everyone has like 0, 1, or 2 children. There's nothing like that within this problem. There's nothing that indicates that. It was just chosen to be drawn like that in this problem. So that's just something to think about. Maybe don't force yourself down that pathway. Try to keep it generalized and saying, okay, this is just a graph, and this is just one such way of drawing the graph. Okay. All right. Again, here they want to draw it like a tree, and it's not necessarily that. So let's do this problem because it's a little bit more, I guess, complicated than this one. So I'm not going to draw it like this, just to signify the fact that you don't have to draw it like that. And drawing it like that might actually lead to, you know, a thought process that's incorrect. Okay, so we have our edges, we have our nodes, so we have 6 nodes, right? So that's how you kind of look at this. So we have 6 nodes. So I'm going to draw those 6 nodes. 1, 2, 3, 4, 5, 6. All right, 1 connects to 2, so I'll put 1 here, 2 here, and there's a connection between them. All right, 1 connects to 3, so I'll put 3 here, connection between them. 2 connects to 4, I'll put 2 here, 4 here. 3 connects to 5, okay, I'll put 5 here, 5 here, and 3 connects to 6, okay, and I'll put 6 here. So there's nothing in this problem, right, that makes this look like this, right? You could pull any node up and make that the root if you wanted to make it weighted like this. It's just a graph, right? It's just a graph. There's nothing really special about it except for there's no cycles. It doesn't necessarily have to look like this, and that's going to help you think about how you're going to solve this problem, okay? Now, the first thing I'm going to do, dude, I hate, why? I don't want to be connected to the, you know what I mean? It's like, I don't even want that. Dude. Ha! Okay, so the first thing we're going to think about in this problem, right, is, well, obviously, there's something important about prime numbers here, so we should probably close this out. Dude, it's so annoying. Like, yeah, load failed. Because so what this app does, just a little tangent, is it tries to force you to use the cloud solution. That way they can charge you for using cloud storage in the long term, even if you have sufficient space on your machine. So they constantly are forcing your notes onto the cloud and being like, oh, you're using up all the cloud. It's like, I don't want to use the cloud. Whoever told you that I was even interested in using your cloud solution? Okay. So that's unfortunate because now I'm going to have to redraw this. It's so irritating. Okay, so I'm just going to draw it like they drew it now. After I made that whole statement about how you don't have to do that, well, I'll make it a little bit different. Okay, 2, 4, 5. Okay, so here's the graph again. I do apologize. Now, since we're dealing with primes, we should probably label things that are primes and things that are not to think about, okay, what do the solutions probably look like within this problem, right? So 2 is a prime, right? 5 is a prime, and 3 is a prime. 1 is not a prime because primes have to be greater than or equal to 2. Just a little life lesson for you. And 4 is not a prime. Okay, so that's kind of what I'm going to label here, right? Not prime and prime. All right, so this is not a prime, and red is a prime. Okay. Now, this isn't even the right example. Oh, man. Oh, whatever. We'll just do this one then. Okay, so there's 4 paths here. How do they find those paths? Well, you know, we can start thinking about them. Well, this is a path here. All right. So that's one of them. Also this. That's 2 of them. This alone is a path. So that's 3 of them. And this is a path. So that's 4 of them. All right, so these are our 4 paths in this scenario, right? Path number 1 here, 2 here, 3 here, 4 here. Okay, so those are our paths. Makes sense, pretty simple, right? And then you'll notice that, well, you know, the situation's all true, right? We have 1 prime in each path. Okay, so how are we going to solve this? Well, I think the best way to solve this problem is to kind of walk through building a tree, like just arbitrarily building a tree with primes and not primes and thinking about, okay, what does that mean about the solution if this situation? What does it mean about the solution if there's this situation? There's really not a lot you can gather from the examples, except that, the obvious things that you already understand, right? That, every path has to have a prime, okay? So we're just going to start by making kind of arbitrary examples and then thinking about what those indicate about the solution, okay? Now, what I mean by that is, well, let's just start with a blank slate and think about what certain combinations of values would mean for the solution, okay? Now, I guess the first thing to think about is, well, every path has to have a prime, right? So maybe we should look at the primes, and for each prime node, think about all the paths that node can create, okay? So every path needs a prime. So look at every prime and discover the associated paths. Okay? And what I mean by that is, well, let's make this smaller. We look at a node, right? And we say, okay, this node is a prime. This red node here. Okay? Now, how many paths can this node create? Well, nothing right now because it's not connected to anything. And let's just arbitrarily draw a system of composite numbers that it can, non-prime numbers, right, that it can connect to. All right? And then I'll just kind of arbitrarily draw these out. So let's say it looks like this. Something somewhat complicated. Now, what paths can be created associated with this system that I've just created, right? Where this is the prime and these are the composites. Well, there's a lot of paths, right? I can create this path, that's 1. I can create this path, that's 2. I can create this path, that's 3. And I can create this path, that's 4. All right. I'm going to make these smaller so you can signify that I'm not talking about the... All right, so there's 4... Sorry, there was a noise in my house. There's 4 paths in the situation that I can create, right? And you'll notice, well, that's just the number of nodes in this system that I'm connected to, right? Because, the truth of the matter is, right, that I can create a path for... Change that back. I can create a path for any of these nodes, right? I can create a path here. I can create a path here. I can create a path. Any of the composite nodes that I'm connected to in the system, I can create a path connecting to them. All right, so if I'm connected to 4 nodes, then I can create, if I'm a prime and I'm connected to 4 composites, I can create 4 paths. Okay? So for a prime, right, I guess our first observation, maybe we'll put for a prime, I can create paths to each of the composites I'm connected to. I'm not even gonna. It's just so stupid. It looks so bad. All right. So there's that case. What if we added another, one of these prime numbers arbitrarily, right? So if I put another prime here and I connected it, well, they can share the nodes, right? But, it's the same thing here, right? I can create a path for this as well now. I can create a path for this. I can create a path for this. I can create a path for this. So they can also create 4 paths. Okay, now this might seem kind of like silly while we're doing this right now, but it's going to kind of indicate something about the solution here. Okay? Right? These primes are like, they're plugged into this system of composites. So for all the composites inside of here, they can create a path. Right? And of course, we can't create this path because it can't have two primes. Okay? Now, the next thing we can think about is, well, okay, what if there were some maybe primes over here? Let's just say there was one prime over here. Or let's just do a path like something a little like that. What would this now indicate? Well, all these paths, nothing changes for this node here. Nothing changes for it. And why is that? Well, he can still create, you know, these paths going in, right, like he did before, but he can't create that path because that path would have two prime numbers. So you can kind of think of the prime numbers as being like walls, right? This red prime number is only directly connected to these composites because this prime number separates them, right? This prime is like, I have these four composites that I can create four paths with, but I can't connect these two over here because I'd have to go through another prime. And since this is a tree, there's no other path to those nodes. So this prime is cutting me off, so I don't have access to this system over here. Okay, so that's a good compartmentalization because that might indicate something about the efficiency here, right? I don't need to look at all these nodes over here for this prime because there's another prime in the way, right? So I can't get a path to it because there's another prime that's going to create a path with two such primes, which I can't allow to happen. Okay, so there's nothing new for this system over here. What is new is, well, now this guy, what is a new situation is now this has new sets of primes that it can connect to, right? Because there's two to its left. But even more than that, what else does this now have? Well, now that I have two arms, right, I can connect these together, and it actually gets pretty messy, right? Because now I'm going to get way more than I can even enumerate easily, right? And I can connect these. Oh, shoot. I can connect these. Right, for each of these paths of one, I can connect this one to it. So I can do this one, and this one, and this one, and this one, and I already forgot if I did all. And then I can do the same thing for this. So I could do this one, and this one, and this one, and this one, right? So since I have two arms, I can mix and match for each of my arms, right? This red node now doesn't have to just think about, okay, people to my right and people to my left. I can choose some from my left and some from my right and make a path like that, right? Any of the nodes from my left, I can make a path to my right, etc. Now, the other thing to think about is, well, since this is a path, right, what if I had this situation here? Well, in this case, I can't make a path that goes like this, but I can mix and match. I can make a path that goes here, and I can make a path that goes here, and I can make a path that, like, you know, goes, oh no, that's all of them, right? Like that. Or I can do direct paths, right? So I have a lot of options here. So how many paths do I get in this scenario? And again, right, this guy cannot go and track the system, right? These nodes can only think about the composites that are directly connected to them. Whatever's happening in this other universe over here, right? I'm going to use a cloud to represent this other universe. This node has no information about that. It doesn't matter. It can only think about the things that are directly connected to it. And how many paths can it create with the things directly connected to it? Well, let's take this system, right? And let's think about it in more general terms. The first thing we're going to do is, like, you'll notice what we care about is the number of nodes that exist in this system, right? So what we're going to do first with this graph is we're going to convert it into a new version where all we care about, right, is the number of nodes that are in between two primes. So we have a new super node here, a super spreader. We'll make it bigger to signify that it's a separate node. And all it has is value 4. And this will have value, these will be the same thing with value 2. Why did I do it like that? Oh. All right, there'll be one here and one here. And these will both have value 2. Right, so the thing is now is we don't need to think about, right, we don't actually need to think about how these composites in this system, right, are orchestrated. Like if it's like 4 like this, or 4 like this, or if they're a straight line, because I can create paths to all of them, right? I just know that if there's 4 composites in this area, no matter how they're set up, I can connect to all of them with one path for each of them, right? So if there's 4 composites and they're all random, it doesn't matter how they're set up, I can connect to each of them and create a path. The way that path looks is independent. So I can kind of take all those paths and figure out how many nodes are there, and then just think about it in these terms, okay? And this will simplify things. So the first set of paths for each prime, right, is each prime can look at its individual set of paths and say, okay, here, using this system, I'm going to get plus 2 paths, right? Because, again, I don't care how they are. I just know that there's a path going in here to one of them, another path in here going to another one. Using this system, I get plus 2 paths. This red one using this 4 system is going to get plus 4 paths. This red one using this system is going to get plus 4 paths. And then, of course, there's going to be other things going on over here. But we're not going to worry ourselves about that. We're just going to look at this specific case to make it a statement about how this problem works, okay? So those are kind of like the direct paths, right? You get these direct paths gains by using these individual systems. But what you can also get is mixing and matching, right? Because I can use one from this path and one from this path, or one from this path and one from this path. And if you actually were to enumerate how this works, using this composite path here is going to give you plus 2 times 4. Okay? And the way that works, right, is, well, if you look at this here, right, if we look at this again, we can do, for this one, I can create a path ending here, 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 right? Because I can do a path like this, path like this, path like this, and a path like this. Okay? And then I can do the same thing for this one, a path like this, a path like this, a path like this, a path like this. So that means for each of these, I can use all of these. So for the one, I can use 4. For another one, I can use 4. So that's 4 plus 4, or 2 times 4, right? So you just multiply them together. I also get another I'm going to do another set here. I'm trying to use a unique color. For this one, that would mean that I get another plus 2 times 2. And then is there anyone that I'm missing? Oh, yeah. And then if I use this path, I get a plus 2 times 4. Right, so we have the easy paths that are really easy to recognize, which are just like direct. Like I go here, I go here, I go here. Right, I use this system, I use this system, I use this system. But then I can also choose 2, combinations of the things that I'm connected to. Right, I can connect these arms together, I connect these arms together, and there's still just one path, such a system here. So that's kind of how this problem works, right? We take this system, we find the primes, right? And then we discover how many composites are in the individual bundles, right? So this system here is in between primes. So we find the number of composites there. We find the number of composites here, the number of composites meaning non-primes. And then we convert it into this kind of graph where we know, okay, this is the number of primes, this is the number of composites here, the number of composites here, the number of composites here. And then we just look at each prime and we look at its neighbors and discover what we get for the solution, right? So Once we have this, we look at this red node and we say, okay, I get +4 here, so I +4 to my solution. I get plus whatever here. I add that to my solution. I look at the next prime. I say, okay, I add 2 for this solution. I add 4 for this solution. I add 2 for this solution. And then I have to add, you know, some combination. So how do you do the combination here? I guess would be the next little thing we need to address quickly. Okay, so if you had a prime, right, and then let's just say you had a bunch of systems that it was connected to, right? Because what you don't want is to do a choose 2 and then look at all combinations of 2, because it's going to start getting computationally exhaustive, okay? So that can blow up your computation. So you need to find an efficient way to look at this node and look at all the combinations of 2 things you can choose without doing like an n-squared operation. All right. So let's just say this was the case here. And these all had generic values like, I don't know, A, B, or let's do lowercase. A, B, C, and D. And all these systems were connected to this prime. So what are all the solutions that you can do here? Well, I could take A, right, and then multiply it with B, right, and that would specify this path. Right, I could take, so that's 1. I could also get the result of A times C and A times D. So those are these paths, right? So this is A times C. And this is A times D. Okay. But then I could also do BCBD, right? So I could also do plus B times C plus B times D. So those are, I'm going to run out of colors here, so maybe this isn't the best idea. B times C and B times D. Right? And then finally I can do plus C times D. All right, so that would be just for 4. Notice how there's a lot of operations that we're having to do now, right? And you'd have to do choose 2, right? Because for every prime node, it connects to all these composites, so I could choose 2 of like my branches and be like, okay, choose any 2, multiply them together. It's gonna not scale very well, right? This is C times D. I don't want to use the same color, you know. Don't be so unoriginal. C times D here. Okay, so is there a way we can play around with the math here to try to find a way where it's not like n choose 2 and it's then a little bit more efficient? Well, you know, if we look at this, we can factor out an A. So that's A times B plus C plus D. I'm just factoring out an A of this top. So A times B, A times C, A times D. So I'm pulling the A out. I'm going to pull the B out of the next term. And then I guess pull the C out of the next term, but it's just one thing. Okay. Right. So so if you notice, if I'm connected to a system of 4 things, right? I do A times 3 things, B times 2 things, and C times 1 thing. Right? So all I got to do is find the sum of this. So if I take the sum, if I say, take the sum of, I don't know what to call it, but let's just say, let's call it big X. I don't know. Big X equals A plus B plus C plus D. Well, all we have to do is multiply A by X minus A. And then we add in B times X minus A minus B. And then we add in C times X minus A minus B minus C. And as long as we update X at each of these operations, we say, okay, multiply A by X minus A, add that to the solution. So then this would just be the new A and be minus B. We'd update X with that now. And then that would mean this is just that minus C. So we don't need to actually like subtract everything every time, right? We can kind of do like a rolling prefix sum idea, right? We find the sum of the system, we multiply it by A, we remove the A. We multiply it by B, we remove the B. We multiply it by C, we remove the C. So now it's just linear with the number of neighbors that I have. So for each of my branches, I just add one thing. Instead of having to look at, you know, some combination of all two things, looking at all two combinations and adding them together, right? We know that, okay, instead we can just look at all the branches once instead of looking at a n choose 2 combination of branches. All right, so with that said, let's go ahead and get right into this, okay? So the coding is actually probably one of the hardest parts of this problem, right? Because there's a lot of coding that's going to be involved in here. So we don't really care what the values are. We just care if they're prime or not, right? That's why I painted them red or painted them green. So we probably, you know, there's a lot of things we got to do here. So we're definitely going to have our solution res that we're going to return at the end. Trust me, it's going to get a lot more complicated than this. But we have res equals 0, and we're going to return res at the end. So this is what we're going to populate. Now, we need some way to find, you know, all the composites that are in an area, right? And all the primes that are in an area. So we definitely need a way to know how do we find a prime, right? Now, the fastest way to find a prime is using a sieve, I think it's called. But I'm blanking on the code right now of how to do that. So I'm just going to do a simple is prime, right? So the simple way of finding out if a number is prime is you say, well, if x is less than 2, then it's not a prime for sure, right? And then you look at I in the range from 2 to, I guess, plus 1. Because you can do the square root of x, and you can figure out this math and how this works. I'm not going to go over it. If x mod 2 equals 0, if x mod I equals 0, that means it's not a prime because it was divisible by something less than it, greater than 1. So we return false. If it's able to get through this whole thing, we return true. This is not the fastest way to find a prime. I'm just being completely honest. But, you know, that's what we're going to do to make this work. All right. And then let's say we have a value array, which is the value if something's a prime or not. Okay. So we'll just make that a default dict. And then set the default value to 0, meaning that it isn't a prime. All right. Or I guess false. I don't know. All right. Now let's build our actual graph. So we'll call it T for tree. And then we'll make it, why don't we just make that a default dict too? Why not? You know, why deal with anything? Okay. You know what? Let's not make it a default dict because we already know the value of n. Technically, we don't need to make this a default dict either because we know the value of n, right? So this would just be 0 times n plus 1. We'll do n plus 1 because there is no value 0, but we'll just leave that alone so we don't have to, like, you know, offset everything by 1. Okay? And this would be blank for blank in range n. So we're going to create adjacency lists to populate each of the tree. We look at each edge and edges, and we're going to create this tree now. So we're going to say T of u, we append v. T of v, we append u. This is just a standard way to take these edges and convert into a tree. And then we're going to say, well, if I don't want to run is prime over and over again to find out if a number is prime or not. So annoying, man. I can't. Well, we'll just do -1. So if the value at u equals -1, that means we haven't figured out if it's a prime or not yet. So we say v of u equals is prime u. And then we do the same thing for v of v. All right, so that's going to create our adjacency list, and it's going to tell us if everything's a prime or if not, everything is not a prime. So at this point, we've gotten this graph, we've gotten this system into, you know, the diagram where I showed, where, you know, there's green nodes and there's red nodes, and that's about it, right? So we've pretty much taken this and turned it into something that's just a little bit simpler for the sake of solving this problem. Okay. Now the next thing we need to do is we need to look at all the values, right? So we're going to look at all the edges u in range 1 to n plus 1. So we're going to look at all the edges. This should be n plus 1. And what we need to do is we need to find out, okay, if this thing is not a prime, so v of u equals 0, we need to look at all the bundles and figure out, okay, how many like values are in this system, right? When we were looking at, maybe I shouldn't have gotten rid of this. But when we were looking at this system here, right, we need to figure out like, okay, how many primes are in this area? I mean, how many composites are in between primes? So what we can do is when we start going through, we'll start looking at things and saying, okay, this is a prime, so we're not going to look at it. Then look at this thing and color all of the composite values in the range and say, okay, we figured out there's 4, so we can do DFS, and then we'll label all of these 4. Right? Then we'll look at this one and say, no, that's not it. We'll look at this and say, oh, it's a prime, so then we'll color using DFS everything, find out that it's 2, and then color them all 2. Okay, so that's basically what we're going to do to make this work. We have to go fast because I'm worried that I'm going to run out of space on my computer and all this is going to disappear. Okay, so this is 0. We're going to find out the length, or the, let's just call it size of this component equals number of, I'm just going to call it DFS because I don't care. All right. And then we're going to color all those elements that size. So maybe we'll just do this like this so it's a little bit more classy. All right. Now let's make those functions in order to do that. So we're going to have DFS. This is going to find the length of a system. All right. So we're going to say, well, if it only counts if the value of this thing equals 0, right? Because otherwise it's either already been counted for or it's a prime value, right? So if it's equal to 0, then it hasn't been colored and it's not a prime. We're going to return 1 plus what? 1 plus what? Well, we're going to look at all the neighbors, right? So we're going to look at all of our neighbors as long as it's not the parent. So we're going to say sum of DFS of V with U as the parent for V in the neighbors in the tree for U if V not equal P. All right. So that should give us the length of each component. And then we have to color them. So I guess we can return 0 here if that's a problem. All right, and then for coloring them, well, we just take U and then we take a color. Well, I don't want to do this forever. Well, it's okay. If it's equals 0, then it's nothing. Until we don't have to color till after. So then we say if V of U equals 0, we're going to color V of U equaling this color. And then for all my neighbors, for V and T of U, if V not equal the parent, we're going to color V the same color. Oh, so we're going to need something to do with the parent here. Where the parent is U. Right? Because what happens is the way that this tree is created, like there's a node and they're connected to each other. So you don't want to like create a cycle. So if you come from a parent, don't go back up that path. Okay. All right. And then after this, let's just print V to see if this makes sense. Because we could definitely get a lot of like infinite loops and code that doesn't work because this is pretty involved. Illegal target for annotation. What? Does anybody know what the hell they're talking about? Oh, if. Should know that's what I meant. Python, come on. All right, so what? So what is going on here? So it's saying that my V is -1. Yeah, 0 is nothing. 1 is true. Oh, because if it equals 0. So I'm going to make these zeros like this. Zeros and ones. So then the values are zeros and ones instead of, you know what I mean? All right. So okay, now the problem is now that, see, I told you the code would be the worst part. Because, like, how do I know what's a prime and what's just the size of a list? You know? And I don't want to find if they're prime again. All right, so maybe we should label... All right, let's label the primes... Let's label the primes 1s and these zeros. So this is going to get really messy here, but I'm just going to swap these really quickly so you don't have to think about it too much. But now you know the zeros represent that they're primes. The ones represent the sizes, right? So 0, 1, 2, and 3, those are primes. 4, it's not a prime. That's why it has size 1 here. There's nothing here with size 2, so just know that that's what's happening here, right? If it equals 1, that means it's not a prime. If it equals 0, then it is a prime. That's a really ugly code, but I'm running out of time, so I don't want to, go ahead and fix it. Let's just continue with it looking terrible the way that it does, okay? Now what we do is we start populating our answers, right? So we go from 1 to n plus 1, and we say, okay, if it's a prime, that means it's 1. I mean, it is 0 if it's a prime. Ugh. So if it's a prime, what are the solutions that we can get? Well, we need to start enumerating through our neighbors, right? So we look at all of our neighbors. Let's make that big value x, right? X is the sum of all your neighbors. So, well, we can also do it the other way. So let's say x equals 0, all right? Then we're going to look at all of our neighbors v in our neighbor set. And then we're going to say, well, if v of u not equals 0, because if it equals 0, then I have a neighbor that's not a prime. I mean, I have a neighbor that's a prime, so I can't connect to it automatically, right? So if my neighbor's not a prime, then I'd say, okay, well, for res, I get the value of the number of nodes there are to connect to. And then I can also add to res this value times x, and then x plus equal v of v. So if that doesn't make sense, what I'm basically doing here, right, is I'm populating this like combination tree without doing, choose 2 kind of in a linear fashion here. So that's my tablet not responding. Well, it's really not responding. Oh, come on, man. Why is life like this? Why do technology? You hear about those new iPhones? All right, that's good. Okay. So instead of, I'm building x here, right? So I start x here with d times nothing, and then I add in x plus equal d. Then I'm going to multiply by c, then I add in c times d, multiply by b, add in b plus c plus d, right? So I'm just reverse building this x array to get all these combinations for all of my neighbors. And yeah, that should be good, I think. Man, it's a long video. I would never want these videos to be long, but sometimes they're just so hard. C is not defined. V of v of my neighbor. All right. Now we just sit here and pray. Now this solution might be slow because there's the way that I'm finding primes. Yeah, so my solution is a little slow because there's a faster way of finding primes, and I'm not going to do it because I can't remember the exact code, but it's called a shiv, and basically, like, it's a really old algorithm. You basically just jump around. Like, you start at 2, and then you go all the way up to n, and you label all the things that are multiples of 2. Then you look at 3, and then you multiply all the things at 3. You look at 4, you see 4 is already a multiple of 2, so you skip it. You look at 5, and you go on. I'm not going to do all that because this passes, but yeah, so that's the solution to this problem. What is the runtime complexity of this? Okay, let's start with say n is the n, right? We already know what n is. And then m is the length of edges, so the number of edges. Okay, let's look at space first. So we definitely use n plus m space because we create an indice for each of the edges, and then we add them. And then we have to look at all the nodes, and then we could end up looking at all the nodes going down in stack space. And besides that, we're just going to use O of n plus m space because, you know, it's going to be shadowed by the fact that we have to create this tree and create references for all the neighbors. All right, now for time. All right, so this prime function is like square root of n or something for all n. So n square root of n. But let's just say that we did the Chev way, and that's log of n. Okay, and that's just doing the sheave. So you can look up that code. Just look up how to do a sheave prime finding. Okay, now we have to look at all nm pairs in order, all edges. We have to look at all m edges in order to populate the array. For DFS, we have to look at every node, right? We have to look at all the nodes, all the vertices in order to find like what can be colored and what can't be. And for each of the vertices, you go through and you color them once. You know, you find the length of them and then you color them once. So that's 2n. That's another n operations. All right. And then finally, you look at all the nodes again. You do n operations. And then you look at all of its neighbors, right? And then you just do constant finds to get away from n choose 2. So that's another n plus m. So this whole solution is n times log nn plus m plus n. All right. That's all I got for you today, folks. Peace.